In this video, I just want to give you a rough overview on the theory of signals. In particular, I want to give you a hint as to how a signal might exhibit a Gaussian distribution or another type of distribution. Let's start from a signal expanded into a Fourier series. So what is a signal expanded in a Fourier series? Well, it is basically possible to represent a signal written in this form. So we have to add multiple harmonics, sinusoids. This assertion is quite general. You can almost always associate a signal with its Fourier series representation. Then, a statistical tool which is useful to study the distribution of the signal is called the moment. We can have moments and central moments, but let's not get into the details of this. We can use this formula for the generic kth moment of a signal. You see that you have the function x of t, or the signal x of t, inside the formula. So if you put the signal into the formula, you can do some calculations which involve some trigonometry and evaluations of integrals, which are not too complicated to carry out. And then what you get is this formula here. This is quite complicated to understand at first, because you see that you have a summation, and under the summation symbol you have some kind of conditions to be satisfied. So the sum of all those indices should equal 0. Those indices can be either positive integers or negative integers, so you can also get a 0 when you sum them. And the summation will be carried out only if that condition is satisfied, and also if the indices are non-zero. As I said, this is a general overview, so that I don't expect you to understand all the mathematical details behind, but I think it's important because this might help you understand mathematically what I'm trying to get across to you in this video. Now, the moments are important because from the moments you can reconstruct the distribution of the signal that we will call P of x. So this is the probability density actually, not the distribution. So let's try not to get confused. But never mind, the probability density of the signal, which can help you study the distribution, can be written in this form. So you can see that P of x depends in quite a complicated way, okay, but depends on the moments. So from the moments you can reconstruct the distribution. In this case, as I said, P of x is the probability density. Now, here comes the subtlety, because there are some assumptions which involve some technicalities, and I don't want to get into the technicalities here. I have written a PhD dissertation in which these results are explained more rigorously, and I also have a course on the central limit theorem derived from stochastic processes, but I don't want to talk about that now. I'm not interested in promoting anything like that. I just want to tell you that it is possible to motivate more rigorously and explain this more rigorously, but it's not the point of this video. As I said, the point of this video is just to give you the mathematical intuition without touching on the technicalities that usually arise when discussing these topics. But anyway, let's get to the core of this video. If the signal x of t has a narrow bandwidth and its phases are uniformly distributed, it is possible to show that the moments have the following form. So that complicated formula that I gave you earlier can be simplified to this form. So the odd moments are 0 and the even moments have a dependence upon the second order moment, which is the variance. And if you put this expression into the more complicated expression for the probability density that I gave you earlier, this one, then what you get is none other than the Gaussian distribution. So when I derived this result in my PhD dissertation, which by the way I was not the first one to derive this result, it was already present in the literature, but I derived it quite intuitively by following some steps, some mathematical steps and assumptions. I was really fascinated by the beauty of mathematics and these kind of assumptions that led me to the beautiful Gaussian distribution. And in order to let you understand a little bit more about those complicated formulas that I showed earlier, if the signal x of t has only one harmonic, meaning that basically it is a sinusoid, then the formula for the moments yields this result. So also in this case, Odd moments are 0 and even moments depend on the amplitude of the sinusoid. Then, if we use this formula for the moments and we input this formula into the formula for the probability density, what we get is this probability density here, which is none other than the probability density for sinusoids. Of course, if you want to know more about the details that I basically hid under the rug, you can feel free to contact me or just take a look at my PhD dissertation. It's just written in the first part of the dissertation. Or you can check out my course on the central limit theorem derived from stochastic processes. But as I said, it's not the point of this video. I just wanted to show the beauty of nature sometimes, because behind all these mathematical details, there actually is the beauty of nature.